Welcome you all into your own YouTube channel of Rachna Institute of Technology for the unlimited practical and theoretical knowledge of the construction industry. So let's start with our video. This is the third video of our series Design of a Column. So if I'm having a request, if you have not seen the video number 1 and 2 of the series, first go and watch the same. You're going to find the link on where the green color is blinking, so that all your concepts should be crystal clear. So let's see what exactly we are going to see in this video number 3. In this video, we are going to design a complete structure of a multi-story building, right? We are going to design a complete column in different respects, so that you are going to get a complete idea how to design a column for a multi-story building. So let's start with a video. So before going for the design of the column, I will want to share you some of the basic concepts, so that your design or your design process is going to become very simple for you. Before going for any of the step, you need to remember very important point. Whenever we are going to start with the designing of a column, we need to start from a top and then we are going to move to the bottom. The first step is calculate the effective span and the load on a column. We need to do for every floor, whatever the total number of the floor into my building. So effective span means, for example, if you're referring the working drawing or any kind of a numerical has been given to you. So if the just take an example of, we are going to consider a load on my column from beam. So if they are given the inner to inner distance of the beam, so that will be a clear span. So I need to able to calculate the effective span, means center to center distance between the support, and then I am able to calculate the load on the column. When I am able to do that stuff, I should be able to calculate the design load, that is PU, that is equals to 1.5 times of the load. Second step is design the column as per the calculated load. So once you're done with the calculation of the load, we also done the second second video of this series, in which we have calculate all the loads in a practical way. In that we also seen the load from a beam, load from a slab, load from a self weight of the column, even from the brickwork. So let's move to this part. So design of the column as per the calculated load. So the first step is you need to assume a percentage of the steel, that we are going to refer from the as per IS code. So that we already seen in our video first part. Second is, once I am done with the assumption of a percentage of the steel, and I need to be able to relate the percentage of the steel with the gross area of the column. Right? Gross area means it's the cross sectional area of the column. So we are going to see in some upcoming part of the video, in which I'm going to put you the link between the percentage of the steel and the gross area. So just take a for currently for understanding the design step, just take a case. You're able to derive the gross area of the column. So when you are able to derive the gross area of the column and you already assume the steel percentage, so you can easily able to calculate the area of the steel in compression. How exactly we are going to calculate? Just take a case. I have considered 1% of the steel I am going to use for the design of the column. So 1%, so 1% of the gross area, right? So I am able to calculate the gross area in my step AG. So 1% of the gross area will be the total area of the steel in the compression, and the remaining part will be the area of concrete, that is AC. Means if I have considered 1% as a steel, so remaining 99% is the area of the steel. So area of the steel will be 99% of the gross area. So that way we are going to get it the stuff. And once we are able to calculate the area of the steel in compression, that is ASC, we need to find which is the respective or the right dia of the bar and the number of the bars, so that requirement of the steel area can be easily fulfilled as per the design. So you may be getting little bit confused by seeing the design step, but believe me, this steps is going to make your numerical or solving the design of the column is very simple. So when we are going to do the design of the column, it is going to be very simple for you to understand the concept. So just be with me, you are going to understand everything when you are going to solve the exact design of the column. Now the third step is design of the link. The most important is when you are going to do design of the link, which I already highlighted, that least of the following. You need to take the least of the following from the value. While doing the design of the link, you can consider the dia of the bar. Generally we used to take 8 mm bar, and the spacing of them will need to be decided by the least of the following. The first criteria is least lateral dimension of the column. So just try to understand with a simple example. I am taking a column size of 230 by 600. So 230 is the least lateral dimension. So that is the first part. Second is the 16 times the diameter of the smallest bar. So just take a case in my column. I am having a 12 dia of the bar, right? So 12 is the least dia of the bar, so 16 times of the 12 bar, that is equals to 192 mm, and the third criteria is the 300 mm. So I need to select the least spacing of the following. So in this list is 192 mm. So when I am now talking about the spacing, so it should be round figure so that it will be easy for doing the practical site. So I will going to take as a 190 mm center to center. So I hope you got a basic idea. So let's directly move to the design step so that all your concepts will be crystal clear. Now that is the most important formula which we need to refer before going for a design of the main column. That is load on a compressive member equals to PU equals to 1.5 W, which we already seen into the step number 1, equals to 0.4 FCK. FCK is the grade of the concrete. AC we have already seen, area of the concrete, plus 0.67 FY. FY is the grade of the steel. So it's mostly FE 500, whatever you're using. So for example, I'm using FE 500, I will take FI equals to 500. ASC is the area of the steel in compression, which we have already seen. So now let me put you the link. If I'm going to consider the percentage of the steel, how it will be going to be linked with the gross area. So let's move to that. Now this is the table for your simplicity, or you can stop the video, or you can write it down the values if you want to take, right? Even if you want to note down the design of the step, you can stop the video and you can just write down the design step if you want to go, right? First understand everything, then you can go step by step and writing down whatever the content you want or you find it interesting. So let me take, I have taken a case of a FE 500 and a M20 grade of a concrete, right? So for that, I have already calculated the value on the basis of the percentage of the steel. For example, if I'm taking 0.8% of the steel, so if I'm going to use that much of percentage in my column can bear a PU of 10.616. So now the question arrives, where exactly this value is derived from? So let me put you a very simple example so that you will understand everything. So I'm using the same formula which I just shown you. So PU equals to 1.5 W equals to 0.4 FCK into AC plus 0.67 FI into AC. So I'm considering 0.8 percentage of the steel, right? So in 0.8 percentage of the steel I am assuming. So I'm just if I'm able to assume the 0.8 percent, I just need to put the values. So 0.4 we already know. FCK I'm using M20 grade, right? AC will be the area of the concrete. So if 0.8 percentage is the percentage of the steel, so remaining is the 99.2 percent. So 99.2 percent of the gross area. Similarly, when I am moving to the 0.67, FI is the grade of the steel, that is FE 500 I am using, so 500 multiply by the ASC, that is the percentage of the steel, area of the steel. So I am considering as a 0.8 upon 100 of the gross area. So here AG will be going to remain the constant and all other are the mathematical values. So I am putting in the formula and I am getting the value PU equals to 10.616 AG. So that is the way we have derived into the table 0.8 percentage steel. We are going to use the formula PU equals to 10.616 AG. That is the relation between the steel of the area and the cross sectional area of the column. So now you understand. Similar way we already calculated for different percentage. Now let's move to the design part, that is most important part. So here we are going to learn, we are going to do the design for RCC frame structure, parking plus 4-floor building. So this is the like architectural view of my building. So let's see the frame structure of the building, right? So I have just to illustrate the purpose, you are able to see the frame structure, right? So we are going to take this column, right? On the grid you are able to see that column we are going to take for a calculation. So you are able to see there is a, on the both of the side there is a 7 meter of a beam, right? And in the front also there is a one beam of a 3.5 meters. So let's take a clear picture from that diagram. So I'm just putting it down. So now I'm able to see there is, I'm just putting the nomenclature. So that is a beam A because both of having a 7 meter of a span, and in the front, that is in blue color which I shown, that is the 3.5 meter of the span, right? So complete beam A having a load of 42 kN per meter and beam B is having a load of 32 kN per meter. So we are going to design this column at the center, which you are able to see. I'm talking about this column. So we are going to design this part. Okay, so let's move to the next. Now I am just putting all the consideration into a question format so that it is going to be very simple you to understand the same. So column of the building is abutted by the three beams which you already seen. Okay, so beam is having a span of 7 meter and having a load of 42 kilonewtons. Now you are able to see here it is a clear span, clearly specified. Next they are saying there is a one more beam in the front, so that is having a 3.5 meter of a clear span and having a load of 32 kilonewton per meter. We need to design a building of parking plus 4 floor. So you can, we are going to consider the FE equals to 500 and concrete grade equals to M20. So design the column at every floor in the following. So while doing the case, or why, for our better understanding, let us take a different scenario so that we can able to understand the designs in a different respects. So just take a case. The first thing which we are going to design, as we already seen, we are going to start from a designing of a topmost floor. So topmost is the fourth floor, so design of a column for a fourth floor. So when we are going to move to the third floor, right, so we have given a condition that, because in practical sense we also understand, we try to keep a one phase of the column as a constant, and we used to do the variation of the other column, so that the one column which we are going to keep as a constant, that we try to flush with the thickness of the wall. So similar way we are going to do for the third floor. So for column on third floor, take one side same as on fourth floor. Right. Moving to the third point, third condition, that is for column on the second floor, take the size same as on the third floor. Means if I'm going to take a size as a same as the third floor, but the load is going to increase, right? So I need to increase the percentage of the steel. If you have seen the first video, everything concept will be going to clear why I'm assuming whatever the stuff is. Moving to the fourth point, that is for column on first floor. So change the size if you want and decide the percentage of the steel. So here we have given an option like you can change the size if you want, and you need to play with the percentage of the steel. Last point, for the column design of a parking floor, we need to give the options and choose one of the most suitable. So generally when you are going to do the design, in generally for a parking space or a first floor, client want to have options. They want to go for, I want a square, circular, rectangular. So in this case also we want to go for options, and then we will go for choosing the best one. So now this is the whole numerical, if I want to say, in the front of you. So in this diagram we are easily able to illustrate the same. So I have put all the details into this. So we are going to design the C2 column, right, that we are able to see. So let's start one by one. The first thing, as per our design step, we are going to calculate the effective span, right? So I'm going to calculate the effective span. So when I'm calculating the effective span, right, and the load on the column, so clear span is given is 7 meter. So I need to take an effective span of a beam is, so I'm having a support of 230 mm on both of the sides. So I'm taking half of from one side and half of from another side. So effective span becomes 7.23 meters. Similarly for a beam of a 3.5 meter, from 230 mm support from this side and that 230 mm support from this side. So effective span will become half of this and half of this. So it becomes 3.73 meter. Now load is already given, that is 42 kilonewton per meter. So it is a per meter unit weight, right? So when I need to calculate the load of complete beam A, so one thing we need to remember, very important, you are calculating the beam C2. This beam we are going to calculate. So this beam is going to get abutted by three beams. So let me talk about the beam A. So one thing I am understanding, if I am having a beam A, so beam A is supported by two columns, that is C1 and C2. So the complete load of a beam is not going to come on my column which I am going to design. So it is going to become half on C1 and half of C2. That is the one of the most important point which we need to remember. Similarly, when I am going to see for the right hand side of a beam A, again I am having two types of a column, so C3 and C2. Similarly, the whole load from a beam A will be divided into two parts. So I am getting a half load of a beam A from right hand side part, and even a half load from a beam A from a left hand side. So when I am going to combine both half of, I am going to get a complete load of a beam A. So that is the stuff we have done. So load from a beam A 42 kilonewton per meter, and the effective span is 7.23. So I am getting 303.66 kilonewton. Similarly, when I am moving to the beam B, so in beam B we are having complete load is distributed into C2 and C4. So the column which I'm going to design, that is C2, is going to only take the half of the load of a beam B. So 32 kilonewton multiplied by 3.73, the effective span. So I'm getting 119.36. So only the column which I'm going to design is only going to bear the half of that, not the complete 919.36 kilonewton. So I'm going to take the half of that, that is equals to 59.68 kilonewton. So combining of that, approximately I'm making into the round figure so that it is always better, and so that I can like if I'm going to do the design, I can take the approximation value in future also. So that's why I'm making into the next round figure, and I'm making as a 364 kilonewton the total load on my fourth floor. So once I get the 364 kilonewton on the complete load on a fourth floor, so it's a typical kind of a structure, so I can easily able to calculate. So for calculating the PU, I know 1.5 multiplied by the total load. So fourth floor equals to 364, we have already calculated here. So that is 364. So PU equals to 1.5 multiplied by 364. So I am getting 546 kilonewton. And moving to the third floor. So third floor is going to have an addition of the load from the third floor plus the fourth floor. So it will be double of the 364. So it becomes 728. So 728 multiplied by 1.5, I am getting 1092 kilonewton. Similarly for second floor, again it will be 3 times of a 364. So I am getting 1092. So 1092 multiplied by 1.5, I am getting 1638 kilonewton. Moving to the load on the first floor, so I am getting 364 multiplied by 4, so that is 1468 kilonewton. So when I am going to multiply with the 1.5, I am getting 2184 kilonewton. Similarly, load on parking floor, so 364 multiplied by 4, I am getting 1820 kilonewton. So when I am multiplying by 1.5, I am getting 2730 kilonewton. That is the load calculation we have done for all the respective floors. So now let's start the design. So let's start the design from a top floor, that is the fourth floor. So design of a column on a fourth floor. So load is, we have already calculated, 364 kilonewton, and PU is 546 kilonewton. So as the load is less, I am going to consider the least steel percentage. So that is 0.8% I am going to consider. So as we are already aware of the table, for 0.8% of the steel, I need to take a total load equals to 10.616. So let me take PU equals to 10.616. So now I am able to get 546, that is a PU which we already calculated. So that is in kilonewton, I am making into the newton. So multiplying by 10 raised to 3. So 10.616 AG. So AG I can easily able to calculate, because if I am going to put the 10.667 in the denominator, I can easily get the AG. So I am getting a AG equals to 51,431.80 mm square. So that is the gross area I am getting for my column. Right. So let me derive what should be the dimension of my column. But if I have taken the least percentage of the steel, so let me take what is the least dimension of the column as per the IS code. So we have already seen into our part 1, that is least dimension is 230 by 230. So if I am going to take the 230 by 230 area, so gross area is 52,900 mm square, and my requirement as per design is less than that. So as per the IS code, I should take minimum 230 mm by 230 mm dimension. So that is very, very simple. Now let's move to the design of the link. So I'm going to consider 8 mm of a link. So now let's go for a calculation of a spacing. So we have already seen the least lateral dimension of the column is 230 mm. So 16 cm. So because as per the IS code standards, we know that for 230 mm by 230 mm, we should be able to minimum use of dia of 12 mm. So there will be 4 in numbers. So that is 12 mm bar dia I am going to use. So 16 times multiplied by the smallest bar. So 16 into 12 equals to 192 mm. So taking approximately as a 190 mm. And the third one is the 300 mm. So least one is the 190 mm center to center. So now we can say easily, we are going to provide a column of 230 by 230 mm with 4 number of 12 mm bars, and using 8 mm as a links at a spacing of 190 mm center to center. Right? So you can easily able to understand why I am taking 230 by 230 if you have seen our first video of design of a column series. Now let's move to the next floor design. So for design of a third floor, we are having a condition that for column on third floor, take one side same as the fourth floor. So we need to take a one side, that is we are going to take a 230 mm side as the same, and we are going to vary the second size of the column. So design column third floor, we already calculated the PU equals to 1092 kilonewton. So in previous on fourth floor we have taken 0.8%. So let's take in third floor 1%. So if taking a 1%, from the table we can know that PU equals to 1092 that we already calculated into 10 raised to 3. It equals to 11.27 Ag that we got from a table. So I can easily able to calculate the gross area. So gross area equals to 96,894.40 mm square. So this is the complete gross area I'm having, and I need to keep one dimension of a column as same. So that is a 230 mm. So let's see 230 multiplied by whatever the dimension is going to come. I'm going to consider that as a D, and I'm putting the gross area. So I'm able to get the D equals to 421.28. So 421.28 is a dimension which is very difficult to put into the side. So I'm going to make as a round figure, that is 450 mm. So now I got the complete dimension of the column, that is 230 by 450. So now let's try to calculate the area of the steel required. So gross area is equal to 230 by 450. So I have already taken that we are going to consider as a 1%. So 1%, so 1% of the complete gross area equals to 1035 mm square. So now that is the area of the steel I need to provide for design of this column. So let's see which dia we need to provide by a try and error method. So by try and error method, so I have written here the required AST is 1035 mm square. So one thing we need to remember, very important, whenever we are going to calculate the area of one dia of the bar, so we can use the formula of pi d square upon 4. You are able to see that is a pi d square upon 4. So why I am not using the formula with the radius? Because sometimes we like forget to get the half of the dia. So better you use pi d square upon 4. So d is 12. For just take a case, I am going to first try with the 12 mm bar. So pi 12 square upon 4. So I am getting area of a 1 bar equals to 113.04 mm square. So if I am going to take, I am going to provide a 6 numbers of a 12 mm bar, right? Because we have seen the 450 mm is the dimension, and we already seen the video, first video, if the dimension of a column, any of the column is more than 380 mm, I need to provide minimum 3 bars. So just take a case, I am providing 6 number of a bars of 12 mm. So the area becomes 678.24 mm square. What is my requirement? My requirement is 1035, almost double of the same. So 12 mm bar is not going to make a sense. So let's move the die of the bar. So now I am going to try with the 16 mm die of the bar. So when I am taking a 16 mm die of the bar, the area of 1 bar equals to, by using the same formula, pi d square upon 4, I am getting 200.96 mm square. So now let me try with a 6 number of 16 mm die bar. So I am getting the total area equals to 1205.76 mm square. So it is again more than that. So more than it is also better, no problem. Know that I can provide the 16 mm bar with 6 numbers. So but let me try with a combination of two different die of the bars, right? So let me try with the 12 mm and 16 mm combination. So what I will do, I will try with 4 number of 16 mm and 2 number of 12 mm. So when I am doing the configuration, so I am getting a complete 1029.92 mm square. So that is almost equivalent to my this much of requirement. So I am going to use 4 numbers of 16 mm and 2 numbers of 12 mm bar. So now go for a calculation for design of the links. So I am going to use 8 mm for spacing. So least lateral dimension is 230 mm. We already seen. So 16 times the diameter of the smallest bar. So again 16 multiplied by 12, I am going to get 192. So making as a round figure, 190 mm center to center, and third is the 300 mm. So least is 190 mm. So that we are going to select. So I can say on third floor I am going to provide a column of 230 by 450 mm with 4 numbers 16 mm main steel bar and 2 numbers of 12 mm bar, 8 mm links at a spacing of 190 mm center to center. So let's move to the design of a second floor column. So in second floor the condition has been given, the size we need to keep same as we have already kept for a third floor. Means if I'm going to keep the same size as of third floor, and we know that on second floor the load is going to increase as compared to the third floor, means I need to play with the percentage of the steel. So as we already calculated, the PU on second floor equals to 1638 kilonewton. So in this particular case we are going to learn how to play with the percentage of the steel. So as the question clearly asks us to maintain the size, but we can change the percentage of the steel. So first we are going to try with the 2%. So when I am taking a 2% of the steel, so PU equals to 14.54 AG. So when you multiply with the gross area, the area of the dimension of the column we have kept the same which we have kept for a third floor, that is 230 by 450. So I am getting 1504 kilo Newton PU equals to, but my requirement is, our requirement is much more than that, that is 1638 kilonewton, and I am only getting 1504 kilonewton. So I need to go for the more, so I need to increase the percentage, so I am going for a 2.5 percentage. So the PU equals to 16.175 multiplied by the dimensions of the column, so I am getting 1674 kilonewton. Now if I am able to see, yes, now I am getting more than what exactly the requirement. My requirement is only 1638 kilonewton. You are able to see here. So now I am able to consider that my requirement is easily able to satisfied. So now I'm taking a 2.5 percentage of the steel. So calculating the percentage of complete ASC into my column. So I'm taking 2.5 percentage, matlab 2.5 divided by 100 multiply by the dimension of the column, that is 230 by 450. So I'm going to get 2587.5 mm square. That should be the total area of my steel. So by try and error method, I am getting 4 numbers of 25 mm bars plus 2 numbers of 20 mm bar. One thing I need to be very specific in this particular case, it is by try and error method. It may be a possible that some of you are getting some other type. You may be saying that I need to go for a 6 numbers of 25 mm bar or some other configuration. You can try with whatever the stuff is. The only thing which we need to keep in mind while doing the try and error method, I should get almost equivalent to area which I required for which I am calculating. For example, here I need the area of the steel approximately 2587.5 mm square. We should get nearby that. So when I am using this configuration, I am getting almost equivalent to 2588 mm square. Now going for a design for the links. So when I'm going for a design of the links, the first is the lateral dimension. So lateral dimension is the 230 mm by 450. So 230 mm is the least one we are having. So that I'm going to consider here 230 mm. So 16 times the diameter of the smallest bar. So smallest wire I am having a dia of bar is 25 mm and 20 mm. So least is the 20 mm. So 16 multiplied by 20 I am getting 320 mm, and the third is 300 mm. So the least is 230 mm center to center. So I can say we need to provide a column of 230 by 450 with 4 numbers of 25 mm and 2 numbers of 20 mm, and providing a 8 mm links at a 230 mm center to center for my second floor. Now let's move to the design of a first floor of a column. So what is the condition we have given for column on first floor? Change the size, right, if you want, and decide the percentage of the steel. So completely dependency has been given on the designer. So let's see. So first we need to see that what is the load on my first floor, that is 2184 kilonewton. So we have already taken 2%. So let me move to the 3% of the steel. So when I'm going to take a 3% of the steel, so it is P equals to 17.81 Ag. So when I'm going to calculate the Ag, I am getting the Ag value equals to this much of value. So now let's try to take a different dimension. So I just want to go for a different dimension, right? Because area is so much huge, because load is drastically, load is more. So let's go for an increasing of the dimension. So I am taking 230 by D. So I want to calculate how much the another dimension of will be. So I am getting D equals to 547. So I can't take a 547. I will make it as approximately as a 550 mm. So taking 3% of the 550, 230 by 550 the column dimension, I am getting the dimension or the AST is equals to 3795 mm square, right? By try and error method, we are going to provide 8 number of 25 mm bars, right? So that is 8 multiplied by 490. So 490 is the area of a 25 mm. So we have already seen pi d square upon 4. So I am getting 3920 mm square. My requirement is only 3795. So I can easily able to provide this much of dia of a bar. Now go for a design of the links. Similarly, the least lateral dimension is 230 mm. So least dia is, now I am going to use 8 number of 25 bars. So only there is 25 mm of the dia of bar is there. So that is the least one also. 60 multiplied by 25, I am getting 400 mm. and the third is 300 mm. So least is 230 mm center to center. So I'm going to provide a column size of 230 by 550 with 8 numbers of 25 mm bar and links of 8 mm at a distance of 230 mm center to center. Now let's go for a condition of a parking floor. Right, so here we are having interesting stuff, because here we need to give the options to the client and we need to select which is the best one. So you are having a choice, whatever you want to choose, you can choose on the basis of aesthetic. You can see able to see in the diagram also. You can choose the one. So design on the column load is equals to P equals to 2730 kilonewton. So we are going to do the try and error and let's choose the best one. So first I'm going to consider the 3% of the steel as the load is more. So I'm going to use P equals to 17.81 Ag. So I'm getting a gross area equals to 1,57,495.78 mm square. So the first option which we are going to have is I'm going to take as a square column. So let's try with the square column. So I'm just going to make it B square equals to 15,07,495. So I'm getting dimension equals to 400 by 400 approximately, because we are getting a value of 396.85. So let's make it an approximate 400 by 400. That is option 1. Now when I'm going for option B, so let me take the similar way which I have designed till now. So we have tried to keep one dimension as 230 mm and we are variation the second one. So let's try the same here. So when I want to do the same 230 by multiply by D, so D which we need to calculate, and gross area we already know. So I'm getting approximately 675 mm of the dimension. Right, so 230 by 675, that is option 2. So I think that is much more like the column is going to be look very differently because 230 by 675. So let's go for option C. In option C, other than taking a 230 mm because it's a parking space, so I'm going to provide a more width of the column, that is I'm other than making a 230, I'm making as a 300 mm. So 300 mm multiplied by D. So other than 675, I'm getting here 550. So now I'm having a option A, option B, option C, right? So as per that is my personal view. It may be you can say you can choose option A, or the client may say choose for option C, or whatever the stuff is, right? So you can choose according to. I have choose the option C because I think that is much more economical and going to look better in all other prospects. So I have chosen the option C. So when I'm choosing the option C, the percentage of the steel I have already considered, that is 3%. So 3% of the gross area, 300 by 550. So I'm getting 4,950 mm square. So by try and error method, I get to know that 10 numbers of 25 mm dia if I'm going to provide, I'm going to get an area of that much, almost equivalent to, that is 4,900 mm square. So now design the links. We are going to get, now till now you are able to understand how we are able to calculate the design of the links. So that is the small stuff I have left for you. So if you're going to, if you can try and you can check the value, it should be minimum 300 mm center to center. So I'm going to provide the column at my parking as 300 by 550 mm, which is having a 10 numbers of 20 mm dia and having a links of 8 mm at a distance of 300 center to center. Now the question is not finished. Okay. Once we have done with the design, the important point is we need to put into the schedule, right? If you're doing designing the column, so you can put the schedule, you can pause the video and you can see how exactly we have put into the schedule and systematic way, right? For a different fourth floor, third floor, second floor. Similarly, you can see for first floor and even for the parking floor. If you want, you can pause the video and clearly see the same. So I hope you learned something new in today's video, and if you really like the video and learn something new, so please like our video and subscribe to our channel for such kind of unlimited learning and in a full-fledged learning, right? So see you all into our next video. Right? You can watch our other interesting videos also, and if you want to give some of the topic on which you are interested to learn, for example the way we have cover for the column, if you want to cover some other structural member, you can put into the comment, and whatever your queries are, let us know in the comment. Our team definitely try to sort it out. Thank you guys, see you on the next video.